In lesson number 11, we are going to study in detail something called rational functions, right? So you've learned about rational functions before, and you learned about the algebra of rational functions, and a little bit about the graphs of rational functions as well. So for instance, one of the families that you are familiar with in in functions themselves is a family that basically looks like the following. It starts off um, from one end and it travels this way, and it continues up and it continues towards the right, and then this other piece looks like that right there. So if you recall, we used to call this the reciprocal, all right? We used to call it the reciprocal family or the rational family, all right? And its graph was 1 over x. All right, so that was the graph of 1 over x. So essentially, we're going to spend an entire lesson dedicated to just that concept of rational functions. All right, then. So before we continue any further with that discussion, though, one thing that we want to discuss, and in the past that students have named, so it's a very specific name. I believe I have mentioned this in an earlier video as well, and it's kind of funny. We called it the tree function, and we just want to kind of study this a little bit more in detail. Well, essentially what happens is you have a function that is similar to 1 over x, right? In the previous page, we talked about 1 over x looking like a function that basically is on both ends of the graph. So now we study something called h over x, and that's just the name that we chose, and that's 1 over x squared. Now in 1 over x squared, basically what happens is the following. Let's suppose you took a number like 1/2, right? Let's suppose you took a number like 1/2. If you were to take 1/2 and plug it into this function, what is that going to look like? It's going to basically look like h of x. It's basically going to look like h of x is equal to 1 divided by 1/2 squared, like that. And when you actually go ahead and you follow with the arithmetic of it, that becomes 1 divided by 1 over 4, and 1 divided by 1 over 4 leads to 4. So like that, we end up with a coordinate, and the coordinate is the following. What we say is when x is 1/2, then the value of y is going to be 4, right? And so what you guys will notice is that when x is equal to 1/2, right over here, notice how its y-coordinate is 4. Now the same thing can be said about negative 1/2. The only difference is it's just on the other side. That's also equal to positive 4, because notice how negative 1/2, when you square it, it'll give you a positive 1/4 anyway, right? Now, using that same logic, we can go ahead and we can plug in a few more values, such as 1 comma 1. Negative 1 comma 1 is what we get out of that. And then if you try the number 2, so number 2 is showing, so I wanted to discuss this with you. You take the number 2 and you plug it into the function, so that becomes h of 2 is equal to 1 divided by 2 squared, which becomes 1 divided by 4, and that's why it says 1/4. So when x is equal to 2, y is equal to 1/4. And by the same logic, when x is equal to negative 2, y is equal to 1/4 as well. And so what you'll notice is this function essentially is traveling in an upward fashion, but as it gets closer to the x-axis, right? Notice how these bottom ends here, it just continues to go flat, right? And in fact, it'll never go underneath the x-axis. So that is one of the qualities of this function. And if you're wondering, and I would wonder the same thing if I were learning this topic, is, well, are you sure it never goes underneath the x-axis? What if I increase that number very, very large? It turns out it doesn't matter how far you go on the x-axis. So please understand, 1 over 100 1 over 10,000, you're basically saying that you're getting really close to the y-axis here, right? You're getting to very small little values of the y-axis, sorry, of the x-axis. And what's happening is this function just simply continues to shoot upwards, right? It's just going upwards like that. That function continues to go up. And on the other hand, if you continue to move on the x-axis, right, in this direction, like 100, 10,000, you'll notice that these values just seem to get very, very small, right? But they never become negative, i.e. they never go underneath the y-axis. So that is a study of what we call the tree function, okay? And on this function, you're going to learn two things. One of them is called a vertical asymptote, and another one is called a horizontal asymptote, okay? So those are two things that we're going to study a lot in detail in this lesson. But basically, a horizontal asymptote is the one that goes this way, and a vertical asymptote is the one that goes in this direction. And so these are basically invisible boundaries that the graph will either come very close to, or basically it might pass it once but never pass it more than that. Okay, and more detail on that in just a moment. Okay, so now what we're going to do is we're going to study that rational function again, right? What we call the tree function, except with transformation. So if you guys recall, we've learned transformations before in a previous lesson. In transformations, basically you can take any function that you like and just it follows the rules of how things are moved around based upon how you change that function. So pretend we start off with the function y is equal to 1 over x squared. Okay, so this is our rational function 1 over x squared. So you'll notice that on this first diagram, in diagram A, essentially all we have is that tree function, okay? And more than that, what you want to start noticing is that there is a horizontal asymptote at y is equal to 0, and there's a vertical asymptote at x is equal to 0. Okay, in the next step, what we're going to do is we're going to transform this function a little bit. And in transforming it, what we mean to say is essentially we're going to take care of the fact that there is a minus 2 next to that x squared, right? Within the x squared itself, sorry. And so that's the next thing that I do. I replace the x with the x minus 2. And if you recall from our study of transformations, what that means is you are shifting to the right by 2 units. So in other words, in B, right, in this graph, what you'll basically see is it's the same graph, but it's been shifted, the same graph as A, but it's been shifted towards the right. So you'll notice that because it shifts towards the right, every one of its coordinates, like for instance, 1, 1 becomes 3, 1 because it shifted 2 units towards the right. So the x value changes. Negative 1, 1 becomes positive 1, 1 because it also shifted 2 units towards the right. So that's one thing to kind of keep track of. Another thing to keep track of is to realize that the x equals 0 is now a x equals 2. All right, so that's often missed by students. They forget to keep looking at that piece as well. But essentially, you have to focus on both parts, right? So that x equals 0 becomes an x equals 2. And notice that the y equals 0, because moving sideways is not going to affect a horizontal asymptote. It's running along the x-axis anyway. It's not going to, it's a line that's basically running along the x-axis. So nothing's going to happen to that just because you moved it towards the right. So that's why you'll notice that this second graph is basically the first graph, except it's shifted, right? It's shifted 2 units right. Okay, now let's go ahead and study the third graph. In studying the third graph, what you have to do is you have to go back to your equations and realize that not only is there a transformation of a minus 2 later on you are adding 1 to that family. And if you recall, that means that you're supposed to move up. Wherever you are, you're supposed to move up by 1 unit. Okay? And that is why you'll notice that now each of the coordinates that we had earlier, we had 1 comma 1 and we had 3 comma 1, are now going to become 1 comma 2 and 3 comma 2 respectively. In other words, the x value now stays the same, but the y value is what is going to switch up, and you'll be adding 1 more unit to the y values. And if you're wondering why is that, it's because of the fact that we just shifted that entire graph upwards. Now, in doing that, please realize that the equation, the updated equation, is shown on the bottom. The updated coordinates have also been written because these are the things that you are expected to be able to do as well. And not just that, here is a third layer of understanding. So things that were not even part of the graph, right? There was a horizontal asymptote. I realize that you don't completely know what that means until the next page, but for now, there was a horizontal asymptote. Think of it as just that dashed line that was moving along with the rest of the graph, and a vertical asymptote. Now notice how, because you move the graph upwards by 1 unit, the horizontal asymptote, which was at y equals 0, is now at y equals 1. But the vertical asymptote, which was already running from bottom to top, moving it further up is not going to change it because it basically continues onwards. It never stops, right? And so your final graph of this rational function is the one that's shown in graph letter C. So I want to give you a gentle reminder that basically as you go through these problems, you're updating a handful of things. The first thing that you're updating is the equation of the function. The next thing that you are updating is the coordinates of the function. The third thing that you are updating is going to be the graph of the function. And part of the graph of the function is, of course, coordinates. But what I mean more specifically is like connecting and making sure that you've got the shape of, here, let me be more specific. You need that particular graph, like actually graphing the function. That would be the most crucial part, right? I don't just need two dots on a graph. And finally, you have to account for the asymptotes, all right? So you're basically going through these 4 things as you're graphing these functions over here. Okay, now asymptotes. All right, so the idea of an asymptote, what does it mean? What does it stand for? So basically, pretend that you had a roller coaster and the roller coaster goes up, right? And the roller coaster then comes down and it continues in that particular direction, right? So if I tell you that there is a horizontal asymptote at this number right here, right? Basically what that means, right, I'll leave it as HA, is basically that even if x were to go really far, and what we say is x were to go to infinity, right? Like you would infinitely go towards the right. Let me write that down. Infinitely move rightwards. That's what that means. So as you infinitely move towards the right, as you continue moving towards the right, that's what a horizontal asymptote means, is you're never going to go past this line right here, which is y is equal to L. You know what? Let me not circle that because then it makes it seem like it's a defined thing, and it's not a defined thing. It's just something that continues onwards. So let's just highlight it. Okay, so you will continue to come very close to y equals L, but you'll never go below it in this situation. Now let's look at the second diagram. It's a very similar situation, except let's suppose that you have a submarine and the submarine is moving in this direction and this is the surface of the water, right? So let's say that this is the surface of the water, and what's happening is the submarine comes up, but it doesn't breach, it doesn't go past the surface of the water, it just is staying below the surface of the water. And so what we're implying here is basically as x goes to negative infinity, as you infinitely go in the negative direction, or basically if you infinitely All right, I'm writing these things down because I know that the notation can be kind of difficult to understand initially. So if you were to infinitely move towards the left, what we're trying to explain is the horizontal asymptote here would basically be the thing that would demarcate that surface of the water, where the submarine decides never to go above that surface. That's all those asymptotes mean. So if you want to look at it in a very simple term, asymptotes basically just mean like things that you can get really close to but never really go beyond. Okay, and so let's do now vertical asymptotes. When it comes to a vertical asymptote, basically it's a similar idea, except instead of continuously moving right or continuously moving left, if you take a look at the third graph, you'll notice that this graph continues to move upwards. All right, so I'm going to write down is it continuously moves upward. And so in this situation, basically, look, these are y values, right? Y equals 1, y equals 2, y equals 3, y equals 4, so on and so forth. So if you think about it, if it continuously moves upward forever, what we can say is it's infinitely going to move upward. All right, I won't write that down, but just understand it to be that way. And then finally, here's another situation. By the way, infinitely moving upward or infinitely moving downward, we kind of treat those as similar cases because take a look at this third one. In this one, basically, one end of the graph is going down, whereas the other end of the graph is actually going up. All right. And once again, in both of these scenarios that you're looking at, these lines right here that I am shading over, these are called vertical asymptotes, all right? So now you see a number of examples about horizontal asymptotes, all right? Horizontal asymptotes and vertical asymptotes. So graph number 1 and 2 was about horizontal asymptotes, whereas graph number 3 and 4 were all about vertical asymptotes, things that you can approach but never really quite go beyond. All right, think of it that way. Okay, now let's go ahead and discuss one last kind of asymptote, and that is called a oblique asymptote. All right, so now that once you understand that an asymptote is essentially something that you can come very close to but never go beyond, this is simply adding a little bit more to that exercise. And we don't study these too much in detail until we come to calculus, okay? But for now, you want to just write down that these are called oblique asymptotes. And the reason why they're called oblique is notice this isn't exactly going straight down or straight sideways. This is actually going diagonally, all right? And so we call that behavior oblique. And essentially, we're implying that this graph is going to come really close to this line, but it'll never go past this line. This line is going to continue forever, and if that graph is going to continue forever as well, it'll just get really, really close to that line. It never actually goes past it. Excuse me. So now what we're going to do, this is the main part of the lesson, is where we learn to analyze a rational function. Okay, how exactly do we read irrational functions? Now the neat thing is, if you tie this in with something that you've learned before, and something that you've learned to do before is analyze polynomial functions, right? So you've learned to work with those before. Recall that it was a 5-step process and it took us a long time to actually go through them. If you can't recall what I'm talking about, basically where we would start with the y-intercept and then we would set up the table and talk about multiplicities and zeros and x-intercepts. So that was a way to graph polynomial functions. So this lesson is not about analyzing polynomial functions. That was previously, right? But what you'll notice is as you graph rational functions, there's a striking similarity between them. Okay, now let's quickly run through the steps and then I think you'll understand a little bit more if you are applying the steps, right? So the first thing that you do in analyzing a rational function is actually the same as polynomial functions. You are going to find the y-intercept. And all that means is you basically plug 0 into the function and see what the y value is. There isn't much to say about that. The next thing that you do is uncommon to polynomial functions, but it happens in rational functions, and it pretty much always does, right? So in this, what you need to do is you basically need to find what is called the domain, right? Now, when you're finding the domain, your job is to go ahead and set the denominator equal to 0, all right? Because recall that whenever in a rational function the denominator were to be equal to 0, the function is undefined. So to find that domain, something that we did in like lesson 1 basically, is something we do now a lot. I've given you a few steps to kind of remember this. Is let's suppose that you have something of the format 1 divided by x minus h. All you need to do is set the x minus h equal to 0 and then go ahead and solve it. And then you can go ahead and write down that the domain of this function is going to be all x values, but x cannot equal that value h like that. Okay? Step number 3 is to go ahead and find any holes and or vertical asymptotes. So we just studied vertical asymptotes a moment ago. We talked about vertical asymptotes, and so now what we do is we kind of extend this idea a little bit. And in vertical asymptotes, basically you are going to look for where the denominator is equal to 0. Now, you might be thinking, wait a minute, I thought you just mentioned this in step 2. So that's the nice part. In step 2, you're basically diagnosing that there's a problem. In step 3, you're figuring out what the problem exactly is, right? Is it a hole or is it a vertical asymptote? Now, a hole is a tricky thing to tell, and I'll discuss this a little bit more in detail when we get there. But basically, to tell if there is a hole at a particular value, remember the word cancel out, okay? There will be factors in the numerator and the denominator, and they need to cancel out. The moment that they cancel out, that's where we say that there is a hole in the graph. Okay, I know that this is quite a lot, but again, in applying it, this becomes quite systematic and quite understandable. In step number 4, what you need to do is you need to find the x-intercepts. When you're finding x-intercepts, basically all you need to do is you need to set the numerator equal to 0. And that is after, I've written it for you in red, it's after you have accounted for taking all the holes out of the graph, all right? Or sorry, finding all the holes in the graph. All right, and finally, step number 5 is to find any horizontal asymptotes. And in horizontal asymptotes, very similar to vertical asymptotes, but we'll have a discussion about this eventually when we get there. All you need to do is you basically need to look at the degree in the numerator and the denominator, all right? Something you know how to do. And if the degrees are the same, then you run through a certain process where you take the leading coefficient of the numerator and divide it by the leading coefficient of the denominator. Whereas if, on the other hand, the degree in the numerator is less than the degree in the denominator, then you're automatically going to make the conclusion that the horizontal asymptote is at y equals 0. Okay, notice how oblique asymptotes have been left out of this, so I generally don't cover them in this course, and that's perfectly fine. We usually talk about them in the next course. And finally, step number 6 is to graph. Okay, so without detailing any more of this, we really need to just get some examples up here. So we're going to go ahead and start with this question, all right? So step number 1. We need to go ahead and find the y-intercept. Now, in finding the y-intercept, obviously what that means is we need to begin by setting the function, putting 0 into it. Sorry, plugging 0 into the function. I said that very awkwardly. I don't want to confuse you, right? So this becomes 0 minus 1 divided by 0 squared minus 4. And when you do that, this becomes negative 1 divided by negative 4, which becomes 1 over 4, which is essentially 0.25. So this is my y-intercept. All right, step number 2. Now what you're going to do is you're going to find the domain. in finding the domain, one thing to remember, and I'm not sure if I mentioned this here, is it's a good idea to factorize first. So you want to go back, if you are copying this, and write down that make sure you factorize first and then tell the domain. All right, I apologize, I did not mention that earlier. So when you are telling the domain in this function, basically what you do is you ask yourself, what is the factorization of this function? And ironically, we have learned, the last time we learned rational functions, we learned how to factorize it too. All right, that was one of the main things that we learned about them. So here's what it's going to become. X minus 1 stays x minus 1. And on the denominator, x squared minus 4 can be factorized using the a squared minus b squared formula. So if you use a squared minus b squared formula, you'll realize this gives you a plus b, a minus b. All right? And so using that logic, the factorization of x squared minus 4 is x plus 2 times x minus 2, like that. Okay? And so now that we've done something like that, we can go ahead and find the domain. The domain of this function, basically what that means is if x plus 2 was equal to 0, let me highlight it. If x plus 2 is equal to 0, or if x minus 2 was equal to 0, what would those values equal? All right. And so in this situation, if x plus 2 was equal to 0, then what would happen is x is equal to negative 2. By the same logic, if x minus 2 were to equal 0, then the value of x would be 2. What we're trying to say is because those two numbers are what cause the domain to become undefined, we need to keep them in a separate spot. And we have to let everybody know that the domain is undefined here. And that is why we write down the following. We make set builder notation, and we write down that x cannot be equal to negative 2 and positive 2, like that. All right? Now moving forward. Step number 3. In step number 3, what we're going to do is we're going to diagnose what's wrong with this graph at negative 2 and positive 2. Why can't we plug in negative 2 and positive 2? So up until now, we've just said, here's the domain, you know. Now we discuss what's the matter with it, right? What's the problem with it? So to do this, the first thing that you want to look for is any holes in the graph. So you're going to check, let me put this in parentheses, you're going to check for holes in the graph. And the way that you check for a hole in the graph is if any of the factors from the numerator and the denominator cancel out. Notice how nothing cancels out. And the x's do not cancel. As a myth that students have in their head, the x's don't cancel out. That's not algebra, okay? So nothing actually cancels out. So you want to just write down no holes, and you also want to write down why. There's no holes because no factors cancel out. All right, and that is why there's no holes in the graph. If you're wondering what would that have looked like, we will get to that point at later. Okay, we'll have another number of functions that we graph, and then we'll talk about this in a little bit. Okay, now let's go ahead and check for vertical asymptotes. So a vertical asymptote is found by basically, let me write down VA. All right, the way that you look for vertical asymptotes is you take what's in the denominator and you set it equal to 0. In other words, you're taking x plus 2 and setting it equal to 0, and you're taking x minus 2 and setting it equal to 0. Now you might say, wait a minute, didn't you already do that earlier? I don't know why I just made parentheses around that. It's unnecessary. Let me get rid of these parentheses. I don't want to confuse you guys. So you're probably thinking, didn't you just do that earlier? And precisely, we did do that earlier. When we were trying to diagnose the problem, we had told ourselves that there was some issues at -2 and 2. And then moving forward, we realized there's no holes at -2 and 2. So basically, the only other thing that could have possibly happened is there are vertical asymptotes at -2 and 2. So we're going to go ahead and conclude that there is a vertical asymptote at -2 and there is a vertical asymptote at 2. No, you don't need to show this piece of work because technically you already showed it, but I'm just kind of explaining to you the thought process behind doing something like that. So there you go. Your vertical asymptotes are at x equals -2 and x equals +2. And one more time, I will remind you that there are no holes in this graph. We checked and we discovered that there are no holes that actually are present in this graph. Now, step number 4 is to go ahead and look for x-intercepts. And x-intercepts is basically where you take the numerator and you set it equal to 0. So notice how to tell vertical asymptotes, you set the denominator equal to 0. Now you're going to set the numerator equal to 0. So basically take the x minus 1 and set that equal to 0. So that's step number 4. Let's make it down here. For the x-intercepts, you take, I'm going to write down x-intercepts. So you're going to take x minus 1, set it equal to 0, and when you solve it, you end up with x is equal to 1. All right? And so this right over here is my x-intercept. All right? Let's just kind of go back and make sure that we have got the domain boxed in, because generally if I'm putting a box around it, those are important realizations that we have as we move forward. So there are essentially 4 important boxes here, 1, 2, 3, and 4, and you can include that as a 5th too. These are important realizations that we're going to need to translate to our graph in just a moment. Finally comes the horizontal asymptotes. So in a horizontal asymptote, basically, all you need to do, let me write down HA, all right? Now you know what a horizontal asymptote looks like, but how do you tell it just by looking at the equation of a function? Essentially what you do is you look at the degree of the numerator and the degree of the denominator. So let's take a look at it, all right? The degree of the numerator is equal, or actually, you know what? Let's make a fraction out of it. Divided by the degree of the denominator. All right? So take a look at it. It's not a mathematical problem. It's just kind of checking. Notice how the degree in the numerator is 1 because there is simply an x there. Right? There's simply an x there as far as things with powers are concerned. So that's a degree of 1. Whereas in the denominator, that's a degree of 2. So what we're looking at is a case where you've got 1 and 2. So notice how the degree in the numerator is lower and the degree in the denominator is higher. That's all you're checking for. So for instance, it didn't matter that it was 1 and 2. What matters is the top one is lower than the bottom one. So for instance, if this was 3 and that was 4, you would still reach the same exact conclusion. And you're probably wondering, what is that conclusion? The conclusion is that there is going to be a horizontal asymptote at y is equal to 0. Whenever you notice that you've got a situation of a low-high, the horizontal asymptote will always, always, always be at y equals 0. So the last thing that we do in graphing these functions is we make a pretty large coordinate plane. So let's take a moment and graph a coordinate plane. Now, one at a time, we're going to go through this problem and we're going to jot things down in the coordinate plane. So let's go to step number 1. In step number 1, what did we discover? That the y-intercept is 0.25. So that's very close to the x-axis. So I'm going to pick a number that's relatively close to the x-axis, and I'm going to label it as 0.25. And basically, we know that the graph certainly needs to travel through 0.25. Step number 2, you basically don't graph anything by looking at step number 2. but it just gives you an indicator of what you're really going to need to put on the graph. So just to help you out, step number 1 directly goes on the graph. Step number 2 does not, but step number 3 is going to go directly on the graph. Step number 4 is going to go directly on the graph. And step number 5 as well is going to go on the graph. So what I mean to say here is step number 2 is just kind of looking at it. Remember back in polynomials, something like turning points, you just looked at it, but you didn't do much with it. So it's one of those situations. Anyways, so in step number 3 now, we know that there is no holes, so we look beyond that. It says there's a vertical asymptote at x equals -2 and x equals +2. So I'm going to call this my x equals -2, and I'm going to make a line that goes straight down. All right. And after I am done making that line, I'm going to do a few things. First off, I'm going to label this as -2 on the x-axis. And more than that, I'm going to write at the top x equals -2. That is not a typo. It's supposed to be x equals that number. That is my first vertical asymptote. My second vertical asymptote is exactly the same distance, but on the other side of the y-axis. So here is my vertical asymptote number 2, and that one is at x is equal to 2, and again, there's my vertical asymptote. Okay, now that we've done that, the next thing that we can focus on is the x-intercept. The x-intercept is at x is equal to 1. So you're going to go to where x is equal to 1, and x-intercept means where does the graph run into the x-axis. So, you know, middle of 0 and 2 is 1. So I'm going to go ahead and make a little coordinate there, jot it as 1, or you know what, more appropriately, 1, 0, right? And so definitely the graph is going to go through 1, 0 as well. Okay, so we are just about ready to go ahead and start graphing. The last thing that we need to account for is step number 5. And step number 5 says that the horizontal asymptote is at y is equal to 0. So I'm going to go to where y is equal to 0. All right, y equals 0, by the way, is simply the x-axis. And you'll notice that I'm graphing over the x-axis, right? So there you go. I'm doing it in red so you can see it quite visibly. And I'm labeling it. I'm going to write down that y equals 0 is a horizontal asymptote. All right, so you know that that's going to be something that's important to us in a little bit. Now, we've got everything ready to go, and the last step that we basically do, and I'll explain to you how you would be tested on it eventually. The last thing that we do here is we open up a calculator. All right, so you open up to your calculator, you go to y equals, and you're going to go ahead and type the graph into your calculator. Now you might be thinking, wait a minute, if we were going to put this in a calculator, why bother with all the things that we've done to analyze the function? And basically, I'll explain that to you at the end of the lesson if I have some time, but there is a reason why you must learn to graph these functions the way that we do. Okay, so you have x minus 1 divided by x squared minus 4, and you go ahead and you hit the graph button. Now, I've got my window set at something else from a different day, right? So what I'm going to do is I'm going to set my window, I'm going to set my zoom to standard first and see if this is sufficient for me, okay? Notice how there is much of the graph that I can't really distinguish, but it's really close to the x-axis, and everything past that is basically just straight vertical lines. So what I'm going to do to make a little bit more sense of this is I'm going to cut this graph off a little bit from all ends. I want to really zoom in and see what exactly is going on here. So I'm going to make this -5 x min, +5 x max, y min -5, and y max +5, like that, okay? And so I can analyze this graph a little bit carefully. So now, here is basically what was happening this whole time in this graph, all right? In this graph, essentially, what you're going to be doing is you're going to look at the graphing calculator, and you're going to look at what we have on our graph paper, and you're going to connect all the dots. So let's start with piece number 1. And I piece these, and you'll see how I do that in just a moment. Piece number 1 for me is that left piece of the graph, okay? Now, so that we don't lose it, one thing that I can do here just to help you understand this concept is I'll take a snapshot of this graph and position it onto our canvas here, okay? So let me just do that really quickly. So there you go. You're looking at this graph and you're trying to position it onto what you have, all right? So here goes. Let me go ahead and start. Um, I'm going to go ahead and start with the first piece, which is this piece over here, the leftmost piece, all right? And basically, you have to use those asymptotes as your guiding lines. If you go past the asymptotes, you are showing me that, Brother Asim, I don't actually understand what an asymptote does. So you come really close to the asymptote, but you never go past the asymptotes, and you make graphs like this. All right, so that's the first piece of the graph. The second piece of the graph is going to be looking like this over here. Now notice how it goes through. It's really hard to tell, but it goes through a point that's really just above the x-axis, and then it goes through what looks like 1, 0. And that actually makes sense because we know it was supposed to look like that, right? And then you kind of just use those as your guiding factors, and then you continue down. Again, if you are not very careful with this, you're basically showing to me that you don't understand what an asymptote does, what a graph does, what's the purpose of certain things on the graph. So you want to be careful with that. So here is that second piece. Notice how it's threading through 0.25 and 1, 0. And then it just essentially goes downwards like this over here. All right, so that is my second piece. And finally, the last piece, which is on that right side of the graph, notice how, again, you use those guiding lines, all right? You use those guiding lines that you've already set up. You have a graph that's very close to x equals 2 and y equals 0, but never quite goes past them. And then like that, you make that third piece. Just a quick comment, you guys will notice that even though there was a horizontal asymptote, 2 of the pieces did not go past it, but this middle piece did, and that happens often, okay? It's possible for one of the pieces to go past a horizontal asymptote, but for the other ones to not go past the horizontal asymptote. Whereas for vertical asymptotes, they can never be passed, all right? So there you go. We have managed to graph everything the way that it's supposed to be on our graphing paper. And this is a very complicated graph. Now, one thing you might be wondering is, wait a minute, explain how you're going to test us on this if truly what you plan on doing is just giving us a piece of graph. How are, if you were going to have us graph it, how are you going to know that we didn't simply look at a graphing calculator to do something like that? So I was looking for a particular eraser. I did not find it. So I just want to discuss this with you. What I do, right, what I do on a question like this, all right, so watch very carefully, is notice how I've given you the ends of the graph. All right, notice how the blue arrows are still present. And so basically, this is what's going to happen. I'm going to give you the blue arrows, but I'm going to have you go through all the 5 steps and then connect the blue arrows appropriately. Now, a person who doesn't understand how does a rational function work, they'll just go in random directions with these arrows. So you can clearly tell they don't understand how rational graphs work. But a person who understands them will know that this blue arrow, whoops, sorry, that wasn't supposed to be erased. That was supposed to be traced over. That this blue arrow on the left is going to connect like this over here to that blue arrow on the right. You see that? Now, one little mistake that students tend to make and then lose points for it, because again, it just shows that they don't understand how these things work. They'll do funny things like make really crooked looking arrows. That's not how it works either, okay? The whole point of an asymptote is something that a graph comes very close to it, but it does not pass that piece. Unless it's a horizontal asymptote where one piece of the graph can actually go ahead and go through it. Okay, now we're going to try another question and basically we're going to run through all of the same steps. But one of the purposes of doing this is to just help you realize some other sorts of things that can happen when you're graphing a rational function. So let's go ahead and go through this a little bit quicker this time. We start with step number 1, and in step number 1, as we talked about earlier, you're going to find the y-intercept. So you're going to find that r of 0 is equal to the 0 divided by negative 12. Now, if you're wondering where did you get that from, basically I kind of jumped a few steps because now we know what it means to plug into a function. So to save some space and some time, realize that 3 times 0 squared is still 0, and 3 times 0 is 0. So 0 minus 0 is 0. That's why I put a 0 in the numerator. In the denominator, well, this is a 0, that's a 0, and you're left over with negative 12. Altogether, the conclusion that leads us to is 0 divided by negative 12. And 0 divided by any number is going to be 0. So there you go. We are done with finding the y-intercept. So if you recall from the previous example, let's kind of just get this out of the way really quickly. So let's move this out of. And from that previous example, the next thing that we did, we told the domain, right? So we go to this example here, and we go ahead and we try telling its domain. So here goes. The domain of this function is going to be the following. First thing that you want to do is you want to factorize it. So the factorization of the numerator is going to be 3x multiplied by x minus 1 in the numerator. And in the denominator, we will have basically you got to factorize x squared plus x minus 12, and two factors of negative 12 that lead us to positive 1, but multiplied to negative 12 are going to be positive 4 and negative 3. So we have x plus 4 and x minus 3. Now, I know that I'm not showing all of my work, and that's simply because of the fact that some of these things we've been through so many times over again that it doesn't require that I show every bit of work. So again, I factorized the numerator and the denominator. So now, to tell the domain, basically what I need to do is I need to look at each piece of the denominator and figure out what is it that's going to cause it to become a 0. So if I take a look at x plus 4, what would cause x plus 4 to become 0 is basically negative 4. And so, as far as the domain is concerned, I'm going to go ahead and write down that x can be all numbers, but x cannot be negative 4, like that. And the other solution to this, basically, if x minus 3 was equal to 0, that means x is equal to 3. So that also needs to be excluded from the domain. All right, so here is the domain of this function. Remember, this helps us because it tells us what kinds of things to look out for. Now we know that at negative 4 we have an issue, and we have to diagnose that issue and figure out what it is. We know that at 3 we have an issue. What exactly is it? It's going to be one or the other. It's either going to be a vertical asymptote or it's going to be a hole. And so that again reminds us of what we did in that last example. We checked for holes. All right, so how do you check for holes? Once again, you basically check if anything factorizes in the numerator or the denominator and then cancels out. So there are no holes in this graph because nothing cancels out. All right, so I'll write that for you again in parentheses. Nothing cancels, all right, from the numerator and the denominator. So there's no holes in this graph. Okay, then that means whatever is left over must automatically be a vertical asymptote. See how quickly we're going through this time. That means there's a vertical asymptote at x equals negative 4 and x is equal to positive 3. So oftentimes I get a question from students and they ask, well, what if there was a hole? Then what would have happened? basically, if there was a hole, we would have taken that particular x value and said that there's a hole at that x value, and the other x value we would have said has a vertical asymptote. Simple. All right. So in the previous example, we checked for holes, and because none of the factors canceled out, we said there were no holes. So once again, we come to the conclusion that there is no holes, but there are vertical asymptotes at the values of -4 and 3. Now, the next thing that we're going to do is we're going to find x-intercepts. Now recall, to find an x-intercept, what you need to do is you need to set the numerator equal to 0. So basically, let's take the numerator, which is 3x multiplied by x minus 1, right? And we set it equal to 0. So when we set that equal to 0, basically one of two things can happen. Either 3x is equal to 0, all right? Or x minus 1 is equal to 0, one or the other. And so the two possibilities would then mean that the x-intercepts, right, the x-intercepts are at x is equal to 0 and x is equal to positive 1. If you're wondering how did you figure that, it's because if you plug 0 into this first box, that causes this to become 0, and 0 times anything gives you 0. If you plug 1 into the second box, 1 minus 1 is equal to 0, and 0 times anything, once again, is equal to 0. So there you go, like that, we have come up with the conclusion that the x-intercepts are at 0 as well as at 1. All right, again, I keep scrolling back just to help you realize the steps. Now, step number 5 is for us to go ahead and note down the degree of the numerator and the degree of the denominator so that we can determine where the horizontal asymptote is going to be. So let's go ahead and take a moment and try that. In step number 5, we're going to look at the degree of the numerator. Okay, so let me write down numerator degree. All right. And then I'm going to write down the denominator's degree. So denominator degree. All right, let's take a look at, in the numerator, the degree is 2. All right, now if you're wondering how did you figure that, remember a degree is the highest power in each particular area. So the highest power in the numerator is 2. That's why the degree in the top is 2. The highest power in the bottom is also a 2. Notice I'm not looking at the coefficients. I'm looking at the degree, the power, okay? And so this is basically 2 over 2. Now, as I mentioned to you earlier, it's not about what the numbers are. It's about the relationship between those numbers. So notice that both of these numbers are same. So a lot of my students called this the same over same case. And so what we mean by that is because it's the case that's the same, here's what you need to do. You need to create a horizontal asymptote at y is equal to the coefficient, the leading coefficient of those particular degrees. So notice how the coefficient on the front of the numerator is 3 because it belongs to the x squared, and 1 in the denominator because it belongs to the x squared in the denominator. So you make a ratio between them and you write down y is equal to 3 over 1. And so we make a conclusion that our horizontal asymptote is at y equals 3. Now, if you're wondering, why is that? Why do we say something such as this? Basically, the idea is because x squared is the most powerful term, and what we mean by that is anything you put into x squared, you put into this x is going to square it. So this one is going to have a greater impact than that one because that one simply is an x, and x squared is more powerful than an x. So in the long run, this function will basically behave the way that 3x squared behaves. It's not going to be impacted in the long run by 3x. And the same thing can be said for the denominator. So when it comes to asymptotes, asymptotes are all about the long run, right? Like what happens in the long run. So for that reason, we are basically looking for the degrees in the numerator and denominator to tell which one is more powerful. In this case, because they were both the same amount of degree, they had the same amount of power. So in that situation, what we do is we take their coefficients, right? And we go ahead and write down 3 over 1, which is equal to 3. Okay, and step number 6 is to go ahead and to graph. So what we're going to do now is we're going to take a moment and go through every single step that matters. Remember, steps 1, 3, 4, and 5 are going to directly give us stuff that we can put onto the graph. So step number 1, the y-intercept is at 0. So I'm going to go to 0, and I'm going to make a y-intercept. All right. Step number 3, remember, step 2 doesn't do anything as far as the graph is concerned. It just gives us an indicator of what things to expect. So step number 3 says that we have vertical asymptotes at -4 and +3. So I'm going to go to some arbitrary spots here on this axis, which I estimate to be -4. And I'm going to make a vertical line that goes straight down. And I will label this as x equals -4. All right. And that is my first vertical asymptote. Then in step 3, the next one is at x equals 3. So I'm going to bring it a little bit closer to the y-axis, so right over here. And this right over here represents the vertical asymptote at x is equal to 3. Okay, so once again, I just fulfilled what step number 3 was asking us about. All right, -4 and +3. Remember, those are vertical asymptotes. Then step 4 says that there are x-intercepts at 0 and 1. Now notice that as far as 0 is concerned, that was already taken care of. When there was a y-intercept at 0, you should know that automatically the x is also 0, right? That's the one thing on the whole coordinate plane they both share. But the other one is a 1. So I need to go to 1, which let's call it right over here. Okay, and you know that the graph is going to feed through there. Now, we are basically going to now do step number 5, and then we're going to start graphing. In step number 5, basically what it says is that the horizontal asymptote is the line y equals 3. So I'm going to bring this line a little bit closer to the y-axis. It's not to scale, right? I'm going to bring it a little closer to the x-axis. Not completely to scale, but we'll have to work with this so that we can fit it into the amount of space that I have. I forgot to put little arrows at the ends of these asymptotes, but basically these continue onwards, right? So like this, I have a horizontal asymptote at y equals 3. And one thing I'd like to kindly remind you of is vertical asymptote, horizontal asymptote. Okay, so that one right there is a horizontal asymptote. Okay, now you want to pick up a graphing calculator and you want to take the moment and you want to type this function into the calculator. Now, here's the neat thing. You can either put the factorized form of the function or you can put the non-factorized form of the function, whichever one you so please. So I'm going to take this non-factorized form and put it into the calculator because that is what I did last time. Please remember to put parentheses around the top and the bottom. So 3x squared minus 3x, I put a parenthesis, divided by parenthesis x squared plus x minus 12, like that. Okay, close parenthesis. And recall what we did last time is we tried to find a good window to see the whole graph, right? And so it looks like the same situation persists over here. We don't necessarily see the whole graph, at least we're not totally convinced. So a good idea is to click on the zoom button and to zoom to standard first, okay? So once you zoom to standard, you'll get a better idea of what's actually happening here. In fact, if you want, you can even zoom out a little bit more if it helps you to understand the graph. But it's completely your call as to what you decide to do. Now, I am going to zoom out a little bit because I really want to see this graph in its entirety. Okay, I'm going to zoom out a little bit. And now I start to see a little bit better. Basically, this graph is coming in from the negative x's and it shoots up. Then it's going to come from the bottom, all right? It's going to touch 0 and 1, it's going to go back down, and then it's going to continue from infinity coming in all the way to, infinity on the x's, right? So what we're going to do is we're going to zoom back to a standard because now we know how to sketch this graph. And here goes. I will go ahead and use this as my guiding lines, all right? And so as I did in the last example, I'm going to take this and I'm going to cut it out so that we have some substance to work with, right? And I'm going to paste it. I'm going to find some space and I'll paste it over here, okay? And I'm going to use this as I'm actually graphing my function, all right? So here goes. The leftmost piece looks like it's pretty far from the asymptote. It looks something like this over here, all right? That is sufficient. I'll accept that because clearly if the asymptote is at x is equal to -4, right, at x equals -4, it really just looks kind of like it's, right, so let me see if I can make it, right, so put a red, so at x equals -4, right, look, that asymptote's pretty far, sorry, the graph is pretty far from that asymptote, right, so that's why I depicted it like that in the picture. Small stuff though, okay? Then let's talk about the middle section. The middle section looks like it's coming in, and then it touches at 0 and 1, and then it goes back down. So that's precisely what I'm going to depict in this graph, is I've got basically, and do your best, right? I've got a function, it's coming in, it touches at 0 and 1, and then it goes back down this way, all right? And so that is the second piece of the function for me. And finally, all right, so the last piece is the piece on the right side, the top right side. So I'm going to go ahead and I'm going to bring that piece in. All right, that one looks like it's pretty close to the vertical and the horizontal asymptotes there. And I'm going to draw it like this. And there we go. We have once again graphed the entire rational function. All right, now let's go ahead and try yet another problem. And this one is, we're going to go again a little bit quicker this time. So write it down. Step number 1 is the y-intercept. All right, r of 0. So you want to do this as quick as possible. Notice that if you plug a 0 here, it becomes 0. That becomes 0, right? The 5x becomes 0. So you're left over with 2. And in the denominator, you're basically left over with -4 because that's x squared becomes a 0 as well. So 2 divided by -4 is essentially what we're talking about here. And 2 divided by -4 is equal to -1/2, or basically -0.5. And there we are. We've got our first one. Okay, now step number 2 is to tell the domain. So let's go ahead and take a moment and tell the domain of this function. To tell the domain, you need to spend some time factorizing this. So let's actually factorize the numerator and the denominator, and this time we'll take the space to do something like that. So in the numerator, that means that you're basically looking for 2 factors of 4, because that's 2 multiplied by +2, which gives you 4, right? So 4 and 2 factors that multiply to 4 are, but add up to -5, right? They have to add up to -5, are going to be -1 and -4, all right? So we understand that, but there's a little bit more, because notice how that front term is not a 1. And because if it's not a 1, we cannot factorize it just by saying x minus 1, x minus 4. So what we're going to do is we'll take the moment and we'll make sure that we get this down correctly. We have 2x squared minus x minus 4x plus 2 in the numerator. And in the denominator, we can factorize that as well. That's simply, oops, sorry. That's simply x plus 2 times x minus 2. All right, we're still working with the numerator though. In the numerator, we're going to have to use some grouping. When we group, we end up with we end up with x common and 2x minus 1. And then we end up with 2 common and again 2x minus 1. Right? We're not spending that much time talking about factorization again. Right? We're just using it because it's a tool that we need to proceed forward. And in the denominator, once again, we have x plus 2 and x minus 2. All right, now last step is we go ahead and we write down 2x minus 1, x minus 2 for the numerator, and in the denominator, we have x plus 2, x minus 2. Remember, the whole purpose of this step was for us to tell what the domain is, right? So for the domain, again, we need to take the denominator and set it equal to 0, and then solve each one of them. So when we do that, here's what we get. We end up with x cannot be equal to negative 2, and x cannot be equal to positive 2. All right, so that was quite a step number 2. But remember, this is going to help us tell many things about the remainder of the graph as we actually go through it. All right, so don't feel bad about that. All right, step number 3. Okay, step number 3 is for us to tell the holes and the vertical asymptotes. Now, this is where things get a little bit more dramatic. Notice that if you go back to the factorized version of this, which is in step number 2, notice that x minus 2 can cancel out from the numerator and the denominator. So I want you to write it in words so you understand why we said this. All right, so since x minus 2 cancels, right? What that means is there must be a hole at x is equal to 2. Because basically you take x minus 2 and set it equal to 0, you end up with x equals 2. Okay? So we come to a very important conclusion, and we find out that there's a hole in the graph, and we're going to have a discussion. What exactly does that look like in just a moment? Well, really quickly, what about vertical asymptotes? Whatever is left over is the vertical asymptote. So look at the domain. When I say whatever is left over, so we already took care of the 2. We know there's a hole there because that's the factor where they were canceled out. But this one never canceled out. So that means at x equals negative 2, there is a vertical asymptote. So we're going to write down that at vertical asymptote at x equals negative 2. All right. And so that is yet another important realization. Notice that, anything that I'm putting in a box is important to us as far as analyzing this rational function is concerned. Step number 4, x-intercepts. Now, whatever is left over, that's what you set equal to 0. Don't set x minus 2 equal to 0. There's a hole in the graph there. That can't possibly be an x-intercept, okay? So you look at what's left over, which is a 2x minus 1. So you take the 2x minus 1 and you set it equal to 0. I repeat, in the previous last 2 questions, we took everything in the numerator and set it equal to 0. And that's because nothing had canceled out from the numerator. But this time around, right, what's happening is the x minus 2's cancel out. So you're only left over with a 2x minus 1. So that's what you set equal to 0. So when you set this equal to 0 and you solve this, well, you bring the negative 1 over, it becomes positive 1, and you divide by 2, right? So you have 2x equals 1, divide by 2, like that, and you end up with x equals 0.5. So there you go. That is your x-intercept at x equal to 0.5. All right. Step number 5. All right. Step number 5 is to tell the horizontal asymptote. So again, let's go back to our original equation. You should always look at the original equation when you're telling horizontal asymptotes. Let me get rid of some of this stuff here. And you got to look at the degree of the numerator and the denominator. So really quickly, because this video is really stretching, the degree in the numerator is 2. The degree in the denominator is also 2, right? If you don't understand, once again, where are you getting that from? You look at the highest power. The highest power is a 2 for both of them. And so you're going to reach the conclusion that because both of these are basically the same, all right, we call this the same case. It's nothing mathematical, it just helps us to identify some stuff. You can call it whatever you wish. What we do is we take the coefficients of those leading coefficients of those powers, and we make a ratio between them. So that makes it 2, and this time the 2 I'm getting is from over here, okay, over 1. And the 1 that I'm getting from is, of course, the coefficient of x squared in the denominator. So that's 2 over 1, and so that's going to give you 2. And so you have a horizontal asymptote at y equals 2. Okay, again, we're going to take a moment and we're going to graph this entire thing. All right, let's start with number 1. It says at negative 0.5 there is a y-intercept. So I'm going to go to, let's suppose over here, I'm going to label it as negative 0.5, and that represents my y-intercept. Remember, step number 2 is, once again, not something that you can put on the graph, but it helps you to tell so much stuff about the graph in the next step. In step number 3, we learned that there's a hole at x equals 2. Now, here is my best suggestion to you. Yeah, again, this is not a vertical asymptote. So what you should probably do is go over to 2. Let's assume this is 2. And just leave a little mark there. Just write down h. Okay, just put h over there. Actually, you know what? You know what? Let me put it in a different color because then it'll confuse you. So there's supposed to be a hole here. Okay, I'm going to leave that there, and then in the end, we'll kind of erase it. All right, so there's supposed to be a hole there. You can't put a hole there until you don't make a graph there. So the graph comes at the end. So we're going to come back and update this at the end. However, a vertical asymptote at x equals negative 2, that we can go ahead and take care of right away. So let's go to negative 2, right, assuming this is negative 2, and let's make a vertical asymptote. Now that is something that we are quite accustomed to. X equals negative 2, and we're calling that the vertical asymptote. All right. Now moving forward, the next thing that we're going to do is we're going to go ahead and graph the x-intercept. The x-intercept is at positive 0.5, so pretty much the same distance except in the positive direction. We're going to write down at 0.5, there is an x-intercept, all right? And finally, at y equals 2, look at step number 5. At y equals 2, it says that there is a horizontal asymptote. Again, I will exaggerate this a little bit and bring it down more close to the x-axis. I know this isn't technically 2 units as far as how we're looking at the graph, but just to kind of save some space here, I'm going to write down that this is my horizontal asymptote at y equals 2, all right? And let me go ahead and just leave a label there that this is my horizontal asymptote, okay? So now that we've got all of these things covered, we can go ahead and consider the graph. So pick up a graphing calculator. All right, let's do this as quick as possible. In a graphing calculator, you want to go ahead and type in to the numerator, remember to put parentheses, 2x squared minus 5x plus 2 in the numerator. And in the denominator, you want to go ahead and type in x squared minus 4. So x squared minus 4, like that, okay? And go ahead and hit graph. Now, this is zoomed to a standard, but it looks like it's a pretty good graph. We're not really going to need anything more than that. This is a pretty acceptable graph. So let me just go ahead and snatch this really quickly. So here is the screenshot of my calculator. All right, and I'll just paste it and kind of move it to something where I don't really need that part. Maybe this part right here. I mean, I need the whole thing, but just to talk about it. So now what we want to do is we want to go ahead and just kind of fit this curve into the spot that we have. So first I'm going to fit this piece of the curve, the top left piece. And so clearly the guiding lines there are these lines over here, x equals -2 and y equals 2. So there you go. That is the first piece. The second piece, watch carefully how I do this. Notice how it's coming in from the bottom, all right? You know that it needs to go through the y-intercept, so it goes through the y-intercept. It goes through 0.5, and then according to the graph, it continues on this way, right? However, remember, we left a little note for ourselves. We wrote that there's supposed to be a hole in the graph at x equals 2. So what does that mean? Basically what that means is when you're drawing that piece, you're going to draw up until 2, make a hole, and then continue on as the graph was telling you to go ahead and graph. You see that? So that's what's so special about this entire example, is I wanted to depict for you what a hole in the graph would actually look like. All right? Now you can review the 5 steps and see that all of those things are now depicted on our graph. So when it comes to holes, you have to do this in the end. All right? It's the nature of the hole itself. You have to do it in the end. If there exists such a hole in the graph, come back at the end and go ahead and place it into the graph. In this last example, what we're going to do is study a different kind of rational function. And before we even start, because you've gotten a bit of experience with it, what you'll notice is in the numerator, there's an x squared minus 1. So that means there's a degree of 2 in the numerator, whereas in the denominator, there's a degree of 1. Okay, so that's essentially the difference between some of the examples that we've done so far and this particular example. But anyways, let's go ahead and get started. So step number 1 is to go ahead and find the y-intercept, right? So that one we've done several times before. So r of 0 is basically equal to -1 divided by 0, right? Because of the fact that if you plug 0 in here, that just gives you 0 minus 1, which is -1. And in the denominator, you have a 0. So notice that this is going to give you something that's undefined, right? That gives you something that's undefined. So the conclusion that we reach there is because of the fact that it is undefined, there is no y-intercept. All right, so that's the conclusion we reach, is there is no y-intercept. All right, and eventually we'll come to realize what the problem was, but for now we're just going systematically through our steps. All right, step number 2 is to go ahead and find the domain. Now remember, in finding the domain, one of the first things that you want to do is factorize the numerator and the denominator to make sure that everything is taken care of as far as holes and asymptotes are concerned. So the top can be factorized from x squared minus 1 into x plus 1, x minus 1 like that. And in the denominator, you simply have an x. So recall that to tell a domain, you essentially need to take the denominator and set it equal to 0. And when you do that, that just means that x can be any number except x cannot be 0. All right? And so notice how earlier we had tried plugging 0 into this function and found that it's undefined. And then later on, the domain is telling you that you can't plug 0 into this function, right? So it's a bit recursive, but it's basically telling us that there was going to be a problem there in the first place. Now, let's go to step number 3, and let's talk about the holes and the vertical asymptotes. So first and foremost, as far as holes are concerned, there is none of them, right? And we've been through this 3 times. It's because of the fact that nothing cancels out from the numerator and the denominator, right? The factors stay exactly the way that they are. As far as vertical asymptotes are concerned, there is a vertical asymptote at x is equal to 0, because that would be the only thing that's in the denominator. And when we set it equal to 0, that's essentially it. All right. Step number 4 is to go ahead and find the x-intercept. Now, to find the x-intercept, recall that we need to take the numerator which is x plus 1 times x minus 1, and we have to set that equal to 0. So when we do that, the two x-intercepts that we end up with are x is equal to negative 1 and x is equal to positive 1. So we end up with two x-intercepts. And finally, the last thing that we need to focus on is the horizontal asymptote. So this is the reason why we essentially have this particular discussion and this question. In step number 5, when you go to find the horizontal asymptote, you'll notice that in the numerator, the degree is 2, and in the denominator, the degree is 1. So you're left over with this special case where basically you've got a higher degree in the top and a lower degree in the bottom. And students in the past have come to define this as a case of high over low, right? So when something like this happens, basically one thing you have to realize is this is going to lead to something called a oblique asymptote. All right, so it's not actually a vertical asymptote at all. This is called a oblique asymptote. All right, and when it comes to oblique asymptotes, that essentially means that it's something that's going to be going diagonally, right? And we'll talk about how to tell that just now. Basically, you have to go through a process that we've learned before, which is called long division. All right, so we detailed this, I believe, in lesson number 8, part 2. And so in long division, basically what you do is you take the x and you divide it into x squared minus 1. Right, so you basically take the denominator and it goes into the numerator. And you ask yourself, how many times does x go into x squared? And x goes into x squared, right? How many times? X times, right? So x times x is going to give you x squared. You switch the sign on it, and then that's going to give you, obviously, a 0, right? Then x multiplied by the, so now the negative 1 comes down. All right, I forgot that step right there. And once the negative comes down, 0 minus 1 gives you negative 1. And now we know that x cannot go into negative 1. Right? If you don't understand this step, then essentially review long division from lesson number 8, right? The video for that. Part 2, right? I believe it's part 2, and it'll tell you about long division. We did several examples of that. So here's what we have. We have a oblique asymptote at y is equal to x, right, minus 1 over x. So basically, the x, where did I get that from? That's from right there, all right? That's the x. And then minus 1 over x is basically the remainder. And finally, the last thing that we essentially get concerned with is we actually don't need the remainder. All right, we don't actually need the remainder. If you're wondering why is that, it's because if x goes infinitely, right, because in asymptotes we're saying that x is continuing on. If x goes infinitely, right, towards the right, you'll notice that this number will actually get larger and larger. And so 1 divided by that number will actually get smaller and smaller. Long story short, basically you don't need that piece right there. All right, you don't need that piece. All you really need is what was your actual quotient, right? So our conclusion that we reach as far as the oblique asymptote is concerned is the oblique asymptote is actually the line y equals x. All right. Now, you are welcome to try graphing this, but it is not necessarily part of the scope of this course where we focus on the graph of it, right? But just because we've spent the last 8 minutes trying to talk about how these work, it's worth our time to just kind of have a small discussion about what do we mean by an oblique asymptote. So we're basically saying that as opposed to before, where you would have had a horizontal asymptote, so you can review some of the horizontal asymptotes, like in this example, there was a horizontal asymptote at y is equal to 2. In the previous example, there was a horizontal asymptote at y equals 3, and the one before that, it was at y equals 0. So notice how either it was a horizontal asymptote or a vertical asymptote. In this question, essentially what happens is it's an oblique asymptote, and it's basically going like this right here. All right, it travels like this, and this is a line. This is actually a line called y equals x. All right, so this is actually our oblique asymptote like that, right? And of course, it's got other asymptotes as well. Like for instance, there is a asymptote at x is equal to 0, right? There's no holes, but we know that there's a vertical asymptote at x equals 0. So I can make a line coming down like this, and that is my vertical asymptote, and that's at x is equal to 0. Let me label that as vertical asymptote, right? So that takes care of that. Notice how we have x-intercepts. I'm just informally going through the steps really to help us realize how is this graph different. So the x-intercepts are diagnosed the same way as before. There is an x-intercept at -1. All right, let's call that -1. Let's call this +1. So the graph definitely goes through -1 and +1. We have that all taken care of. And at this stage, all you really need to do, right, you've taken care of x-intercepts. There is no y-intercept, as we discovered in step number 1. You've taken care of the oblique, the vertical, and all you need to do is basically pick up a calculator and graph the function. All right, so let's go ahead and take a moment and do that. We end up with x squared minus 1, and that's divided by an x, right? So when we do something like that, basically here is what we end up with. We can zoom in a little bit into the center to see a little better about what's happening. So basically, this graph is essentially going through -1 and 1. It does not go through the origin. It just gets really close to that line x is equal to 0, but then it just continues forward, right? So let's go ahead and pull the screen. All right, let's grab the screen really quickly, and let's put it onto our notes. All right, and flatten it. So here's our screen, right? Here's what we discovered, and all we have to do is just connect all the dots. So I'm going to take color here and connect the dots. So basically, this graph is coming really close to the line y equals x, like this, and then it continues in that direction, and it goes up this way, all right, and it goes down this way. So basically, as this oblique asymptote continues, this graph gets closer and closer to it, is what I mean to say. And then the other piece is very similar, right? Notice how it's coming in from the bottom. You thread the needle through the 1 like this, and then it goes that way. All right, so there you go. That was a discussion about that last part of the lesson. Thank you so much, and good luck with the homework.